Thanks for the invitation. It's a pleasure to be here. So, yes, first of all, I'm an alumnus of USINF. So that was the graduation date. I was not here. It was October 2012. Antonio Cadaniga is in the bottom corner, right corner, and that's me. You know, that's a picture taken by Cesare Pautasso. So, yes, I was one of you 12 years ago. Been here for a few years. Now, I'm in Luxembourg, the University of Luxembourg. It's a relatively new university established in 2003. And the university likes to call it international, multilingual, and interdisciplinary. And interdisciplinary is really the key of the University of Luxembourg. There are 4 faculties and three interdisciplinary research centers. And I'm affiliated with one of them. It's called S&T, stands for Security, Reliability, and Trust. But what is the mission of Interdisciplinary Center is to perform top-level research paired with technology transfer. So this is one of the mission is really to fuel the innovation system, the national innovation system, and we do it through a collaborative, demand-driven partnership program. So this is a program that allows for the collaboration between university, S&T, and industry. And this is done by defining a research project in collaboration where we share the cost, we share the IP, and these are research project with the PhD student and the postdoc that work together on the long term for 3 years to solve a problem driven by the demand of the company. And this is this is the standard TRL technology readiness level for research project, and we like to say that the S&T partnership project stands between 2 and 6, level 2 and 6. So we start from a technology concept, proof that becomes a proof of concept, which is first validated in the lab and then validated in the real environment. So deployed at the partner premises at the level of having a working prototype that capture the core of the solution, the algorithm for the problem. Then we leave the rest, so the actual operationalization and commercialization for higher TRL level that goes beyond the scope of research. And as Carlo said, I made in the research group software verification and validation. This was established by Lionel Briand in 2012, and I took over last fall. We are 18 people with a mix of faculty member, postdoc researcher, and PhD and research engineer. And we are proud to say that we have 3 pillars that characterize our mode of collaboration with industry. First, as I said, as part of the S&T partnership program, our research is typically driven by industry needs. We aim to perform realistic evaluation of our solution on a realistic system, and we try to do this in a way to combine innovation and technology transfer. Now, the research topic of S&T spans over 4 areas, so that it goes from requirement quality assurance, design time verification, testing and analysis, and runtime verification. I'm mainly responsible for regulatory compliance and everything that is at the bottom, so security analysis testing, monitoring, specification language and log analysis and anomaly detection, which is actually the focus of the talk. And in all these projects that we go, there are colleagues working in other area, like functional safety of AI-based system, and we have Paolo, and the work, we are exchange, my collaborator exchange with him and his team, for example, on this topic. But in all our applications, we really focus on the scalability of the solution to scale up for the size of the realistic system and on the applicability in the field. And as I said, the focus of today is my research area, which is runtime verification. Now, this is a definition of one of the many definitions of runtime verification, which is also called online testing, just to put it back in a testing context. So so we can say that the runtime verification is a technique that verifies either while the system is executed, so in an online setting, or after the execution end, and we say it's in offline settings. And the purpose is to verify the behavior of the observed behavior of the system against some requirement or some specification. And runtime verification, in my opinion, has 3 main pillars. It's a specification language to express the property of interest. and monitoring algorithm to do the actual verification, and a diagnosis. There is a diagnostic component that explains the reason for a violation of a requirement. And today's talk is set in the context of cyber-physical systems, and the focus on a specific kind of type of properties, signal-based temporal properties. This is mostly part of the PhD thesis of my former student, Shaima Boufayed, and collaboration with Claudio Menghi, who was a postdoc at the time, and Lionel Briand. And as I said, there are three pillars in runtime verification. The first one is specification. And the work that I'm going to present is set in the context of an industrial collaboration with Blackspace OHB. So it's a space system integrator. They at the end deliver satellites, and from the physical hardware to the onboard software of a satellite, and specifically was related to the development of the ISAIL, which is a satellite that collects tracking information from a vessel around the Earth. And the focus is on signal-based temporal properties. What are these properties? Well, as the name suggests, these are properties that are used to define the behavior of cyber-physical system from focusing on the input signal, that the signal read by the sensor, the output signal that goes to the actuators. So what we generically call signal behavior. And why are we focusing on this? Is because typically in the CPS domain, requirements are expressed in this way. And we will see an example now. So here we have the velocity of the satellite along the x-axis shall oscillate within a maximum amplitude of 8,000 kilometers per hour and the maximum speed of 180 millimeters. So this is a specification from a real system. And you see that we have some attributes related to the behavior or the physical behavior of the system. So there is an oscillation that is characterized by an amplitude and the period. But another example, because we are talking about cyber-physical system, is this. When the satellite mode switches from idle to normal, then the angular rate shall reach a value lower than 1.5 degrees per second within 10 seconds. And moreover, the same signal, the angular rate, should stabilize around an arbitrary value c lower than or equal to 1.5 degrees per second. Now, here we have the concept of mode, which is typically something that we see in the cyber domain. So imagine you have a state machine, and you switch from one state to the other, from one mode to the other. So this is a cyber behavior that is paired with a physical behavior. So the angular rate, that is something that you can measure, and it can have some behavior. For example, should stabilize. So there's, for example, some oscillation are allowed, but then should stabilize around a certain value. Now, when it comes to dealing with signal-based temporal properties, there are a few challenges that are interesting from a software engineering point of view. The very first one is how to characterize the feature of signal behavior. So far we have talked about, I made the example of the oscillations. We have amplitude and period. Is this the only way to characterize an oscillation? Or what does it mean to stabilize? Can I have a burst? Should I reach a steady state representation of the signal? So we felt that there was a need for a classification of signal-based signal behaviors features. And then once you know what to specify, so the type of behavior, the type of aspect that you want to capture, is how to specify them. So there are a plethora of specification languages in different flavors. And in the literature, there have been attempts to formally specify signal-based requirements. Are the existing language enough to capture the behavior that should come from an analysis of the first point? And then once we have a specification in the context of runtime verification, then there is the question, can we have a trace checking procedure? Given a trace of an execution, can we check for the conformance of the trace with respect to a specification? So what we did at the very beginning was we aimed to classify signal-based temporal properties. We did this by analyzing the relevant literature and also by interacting with our partner, Blackspace, with their system engineer, so system and software engineer, actually. And we came up with this classification of signal-based temporal properties. So this is you have the classical data assertion. This is something that we see very often. When we write our test cases, typically we write some assertions on data variables, but then there is the part on signal behavior. What kind of behavior a signal can exhibit? So you'll see there is an example of a spike or a bump behavior. We can have oscillations, and oscillation can be increasing, damping, or can be constant. And then there can be a relationship between signals, and the relationship can be functional. So you apply a transformation as a function or a signal to another. Imagine some Laplace transformation, for example, or it can be focused on the order. So we go into a more temporal behavior, and we can capture transit behavior. So, for example, there is the rise time when the signal the signal should reach a certain value or should drop to a certain value, but it can also overshoot. So it goes beyond a nominal threshold that will result in an anomaly. So what we did, we look at the different type of behavior. So this is the first property that I show. It's about the oscillation. So how can we characterize this, and well, we can, for example, reason in terms of peak-to-peak amplitude of an oscillation. We can reason there is a period, we'll look at the different axes. When it comes to spike, for example, there is an article in the literature that it's only about formalization of a spike, how to represent it, and there are different proposals. You can look at the slope of the first half of the spike. You can look at the valley point and so on. So there are different ways, I think 8 or 10 ways of representing a spike or a bumpy behavior in your in the system. And so we try to systematically analyze these behaviors from the literature, from the experience with our partner, and then we to address the second challenge, which is related to the specification language. So we look at how can we express these properties with existing formalism. So what we look at consolidated languages in the cyber physical system community, which is STL, proposed in 2004 by Dejan Nikovic. There is a variation which is called STL star, which contains the Fritz operator. And then right after we started this work a few years ago, there was this proposal by the group of Thomas Einziger, which is the signal first order logic. So basically first order logic targeting signal. So what we did, we tried to characterize the behaviors that we have captured in our taxonomy along with these three formalists. So this is, for example, in SFO, it's first order logic. So you will see some quantifier, you can define predicates and basically describe in a precise way what was captured in the picture, for example, with the presentation of the different valley point and slope. And then this resulted in an assessment of the expressiveness of these three formalisms, which for each type of behavior, you can see, there are, for example, different ways to represent the spike, with the amplitude, with the slope, with the width. You can use punctual derivative, you can use pre-computed derivatives, you can use analytical derivatives, and so on. There are different ways. You can have behavior with monotonicity and so on. And the conclusion was that SFO, being a first-order logic, not surprisingly, could be used to express all the type that we had considered in our taxonomy. And but there were, some STL star is in the middle because it has the Fritz operator, so it can still could be used to pinpoint specific locations in a temporal trace that you can refer to in a specification, while STL fails short, because it cannot. There is no Fritz operator support, so it's the less expressive with respect to these properties. And of course, it's not shown, but on top of the expressive, we also look at the tool support. And SFO, there was no tool support at the time, and as far as I know, up to today. So he had a very powerful language, but with no tool to use for the actual verification. So back. So what we did, we apply our taxonomy to a case study provided by our partner. This is to, first of all, to show the feasibility of expressing requirement as following our taxonomy, our classification of types, and to see also the completeness. So the engineers provide us with 41 specifications from a real system, and this is the distribution. So we notice a lot of functional relationships. This is not surprising because there are there are mathematical functions that are applied to input signal to get some output signal, but there is a lot of many order relations. So it's so there is a temporal aspect in the behavior of the system. Then we also find some spike and oscillation. Then the question is, what can we do with this taxonomy? Well, it could be the basis to start designing a new specification language, for example, by mapping the construct of the language to the property type in the taxonomy. We will see in a second, but it can also be used as a benchmark to assess the expressiveness of existing languages, and in general can be used as a reference guide, for understanding, characterizing signal behaviors. But also, if you look at the table, it's a choice. It was a practical guide for engineers to say, hey, these are the language available, these are the properties that we use. What can I use? For example, there are some tools, and we will see them later in the presentation. So what we did, we focused on the first part, and we focused on the design of a new specification language, because we are still in the context of the first elements of runtime verification specification languages. And then we reflected. So when it comes to designing a specification language, there is always a trade-off, between a more traditional solution, which is foundational temporal logic in many forms, or going for high-level domain-specific languages. This is something that I've been setting for a while, or since the time of my PhD, and this is the dichotomy. And temporal logic is very generic, very powerful, while DSL are high-level and probably limited to a specific domain. They can be. When I was a PhD student, we worked on service-based application, for example, and then you can have a CPS from a point of view of, for example, frequency-based characterization or a temporal behavior, like you see in the example. And then it comes also the syntax, and more complex versus more user-friendly or more understandable, and also the required mathematical background to use this type or formalism or notation. So what we did, so we designed a DSL that we call SB-TEMC DSL, which is a pattern-based specification language based on the types identified in the taxonomy. So from a point of view of the language, this gives you high-level concepts, or you have oscillations with the precise feature in terms of, for example, peak-to-peak amplitude or period. So you can write in a compact way. This is the syntax. I'm not going into it, in the interest of time, but we try to capture the different aspects of the languages. There is a very detailed formal semantics that you can consult in the paper if you are interested. This is AAC 2020. But then we say, what can we do with this language? So we assess the expressiveness. So and how does it fare with respect to existing specification language, in particular STL, which is the standard not only in the research community, but also in the industry. Because, so what we did, so with our partner, with a separate group of engineers, we built a catalog of 101 requirements. This is with the chief software engineer of our partner, and we expressed them in SB-TEMC DSL, STL, and SFO, which was the cool kid in the research community at the time. So these are the results. So we could STL could only express 59 requirements, because basically STL is MTL, with some measured temporal logic with support for predicates on signals. Also on real valued variables. SFO, full achievement, and SB-TEMC DSL performed pretty well. We covered many results. But we have a very specific language. What can we do? So we need to move to the next steps in runtime verification, which is monitoring. So in particular, here we consider the the use of declarative specification, so like specification in a temporal logic or in a equivalent language at the offline stage. This means that we assume to have the entire a trace, a recorded trace of the execution that we analyze against the requirement, and we yield a Boolean verdict. We use some qualitative semantics. So what we did, we rely on some previous work that from another PhD of mine. Actually, Carlo was on the PhD defense, and we're doing it back in 2016 was the defense. The article was published 1 year later at Models. So this PhD student of mine at the time, he worked on introduced the concept of model-driven trace checking. So the idea is that if you have to check a temporal property on a trace, you can reduce this problem to the evaluation of an OCL constraint on an instance of a meta model representing the trace. And of course, the OCL constraint should capture the semantics, should be equivalent to the property of interest. And we made a conjecture that can a model-driven approach, the concept of trace checking signal-based temporal properties, provide a verdict within practical time limits when fed with real-world execution traces. So this was our conjecture that we wanted to prove. And the reason for doing so was we had a very positive experience in terms of scalability for temporal properties, non-signal-based temporal properties, as well as for temporal properties with aggregation. That's from another more combined. Temporal properties with aggregation that are basically based on pattern for service-based application that I developed a few years before. So we were quite comfortable, and what we did, we built this tool, SB times C check, which follow a model-driven trace checking approach. So we have a trace, which is pre-processed to manipulate the timestamp so that we have a timestamp at for each element in the trace. So if no element was captured, we just repeat the same signal value. And then we have a property in our DSL, which is translated into an equivalent OCL constraint. So OCL basically is the equivalent to a first order logic. So you have access to first order constant, in particular quantifiers, and then we yield a verification verdict. And if we look at the complexity of the, you have a question? Yes. So the trace use discrete timestamps, but the values of the timestamps are real values. So I'm not going to show the translation because it's 1,000 of OCL lines that I will spare. What I can say that in terms of time complexity, of course, it depends on the size of the trace. So and it's linear for the majority of the property types. So this depends on the encoding of the semantics of a property in OCL. It's linear for the majority of the type, except for, and it becomes polynomial for the order relationship. Between signals. So this is where we go polynomial. And when it comes to the applicability, so we check it on 18 traces that range from 41,000 elements to 1.2 million entries. And we had 217 distinct combination of property traces, because not each property could be checked on each trace. It depends on which variables are used in the property and which variables are tracked in the trace. And we compare with Bridge tool, which at the time was the state-of-the-art offline trace checking tool for STL that was available, because there used to be AMT by Dejan Nikolic, but at the time that we were doing the experiment, he was retired because AMT 2.0 was being built. So we're in the middle. So in terms of performance, we had 87% of the trace that could be checked within 50, or on average within 50 seconds, so very practical time limits. But in particular, for 99% of the successful runs, so the verdict was provided in less than 10 seconds. We had timeout over 2 hours for all the relationships because of the complexity, and for what we call event-based scope. So when we focus, when we look at the trace, we try to identify the scope of the fragment of the trace in which the actual property should be checked. And this can be characterized by events, so on the occurrence of some events, and in that case, we had some timeout. Then for the comparison with breach, we could only look at the type of property that could be expressed in STL. So it's a subset of the property. So for the property that could be expressed in both languages, our tool finished in 97% of the runs within 2 hours. Breach finished all of them, and it was very fast because the maximum execution time was 0.15 seconds, so very, very fast. While our average execution time was 85 seconds, still acceptable. The main difference is that our tools support a larger set of properties. So the conclusion was that our approach could be seen as a reasonable, viable trade-off between an express specification language, our DSL, and an efficient trace checking tool. But this comes with a penalty, compared to TSTL. So our recommendation is to use the two tools to complement each other. So if you just have to check STL properties, so data assertions on real value-based variables containing trace, just go for STL and with a very efficient tool. But if you have more complex behaviors like oscillations or spikes and so on, then you can use our tool still within practical time limits. Speaking of time limits, I know that I'm approaching the 30 minutes mark, so the last part of the talk is about the last ingredients of runtime verification, which is diagnostics. So when we look at the trace checking approach, I said the tool returns a Boolean verdict. Now the question is a Boolean verdict enough when it comes to a log analysis? When you have a trace and you know that the trace fails, so there was a violation of a requirement, but what can I do with that if I just know that there was a violation? So this is a bit related to the problem of false localization that we have seen this morning. Okay, if there is a fault, I need to know what happened. So we looked at the trace diagnostic. Again, this is a follow-up on the work that my previous PhD student had done. Carlo might remember from the thesis a few years ago, but this is adapted to the context of signal-based temporal properties. And here, we introduced two notions. The first one is violation cause. Try to understand the behavior of the system that led to a violation of a requirement. And the next one is the diagnosis. So it's the additional information that we can collect from the traces, from the context in which the violation occurred, that can help engineer understand the actual cause of the violation. So what we did, we proposed a methodology to define violation causes and diagnosis. And this methodology, in principle, is language agnostics, in the sense that it works can work with languages that have a pattern-based approach. So we apply to our SBTEMC, but there are, if you look at the embedded system that is FRET, for example, from NASA, that is also based on patterns. So we also show how this can be done. But here the focus is a methodology to define a diagnostic approach. So we identified 3 steps: a characterization of the behavior of the system, the definition of the violation causes, and the definition of the diagnosis. Now, I will give you a quick example. Let's assume that we have a rise time property, which says the signal shall rise monotonically reaching value 3. You want the signal to reach a certain value. And then on the right, you see 4 different shapes, 4 different signals that violate this property. So you have the blue signal that never reaches value 3, which is this horizontal bar. So it's always below 3. You have dually, you have the black signal that is always above value 3. Then there is the red signal that reaches value 3, but actually it's not monotonic because we have a valley point here, so it goes up and down, and then it eventually reaches 3. And then instead of, there is the green signal that is quite acid green, so I guess it might disturb your eyes, but sorry for that. But actually, instead of rising, it falls. You can see there is a drop of that signal. So these are possible behavior that with some domain knowledge, an engineer can define to represent in a non-exhaustive way sometimes. So we have to say this is a non-exhaustive process. It's literally based on domain knowledge of how something can go wrong. Once you have this behavior, you can characterize what we call the violation causes. So for each of this behavior, one can write a first-order logic formula. And in the paper, you will find the details that, it's if this formula holds on the trace, it means that there is a violation of the semantics of the original formula for which this formula was written corresponding to the actual property of interest. So what we did, and you will see later just a screenshot, we wrote first-order characterization of all the known violation of the property type that we have in our language. And then the diagnosis is the actual information. So basically, we look at the context and we can see what are the relevant values, the relevant information that can be useful for an engineer to understand the code. So typically, it's the range of values taken by the signal. It can be the range in the proximity of, for example, of a valley point when you had a non-monotonic behavior and so on. So in the paper, this is a TSC paper, you will find a lot of, this is a characterization of the violation causes, as well as of the properties of the diagnosis, and all of these are then encoded in OCL in our tool. And what we did was we applied it. So we look at two datasets. One is proprietaries from our industrial partner. The other one it's a automotive powertrain model that's been used in the Specification community in embedded system. So we got 361 traces, 98 requirements. These are the 98 requirements that we could express in SB terms in DSL. So we got more than 35,000 trace property combinations. Out of this, almost 15,000 led to a violation of the property. And then we also manually add the additional trace property combination because we want to cover different aspects of the languages. And then in 83% of the cases, our tool was able to finish within a minute, was able to provide the diagnosis. And this diagnosis was successful in almost 99% of the cases. So we had some cases in which we could not provide the diagnosis because the behavior was, as I said, this is a non-exhaustive representation of the violation causes. We did not capture that in the language. So what do we have? So to sum up, so we have runtime verification for signal-based temporal properties. We have these three aspects of specification language, monitoring and diagnosis. We build this suite of tools. But there is some ongoing work. So after this, we, in the context of the Cosmos EU project, DevOps for CPS, so which just finished. So we looked at enhancing signal-based properties with the possibility of expressing cyber behavior. So if you remember at the very beginning, one of the examples that I gave was about the satellite mode. We said from idle to normal. One way of representing this is to build an artificial Boolean signal that says, "Oh, this is the state of the satellite. 0 is for idle, 1 is for normal, 2 is for landing, and so on." But actually, it would be nice if you could refer to the state in terms of the actual source code that determine a certain state. So we could say, well, there could be a possibility that we can say that the satellite is in idle mode if during the execution of a certain function in the code, a certain variable is set to a certain value. So this is a property at the code level. So what we did, so with the Pascal command, Josh knows, we tried to build a language that can still express signal-based temporal properties, but it can also at the same time express constraints on the source code level behavior. So function invocation changes to variables. So, and then we have this language, SCSL, source code and signal-based specification language. So the language itself was presented as FAX22. And for a variation of the language, we recently got the paper accepted the industry track, because this was mostly validated with the industrial partner of our Cosmos project. So, and now I have a PhD student, Christina Stratton. Her PhD is fully focused on building diagnosis for this language. So she started with the simpler version of it's called ICFTL, which is without the signal part, just about the temporal behaviors, and now she's working on this. And this concludes my presentation. So here for questions.